So what we can do is we can use log base 10, but I'm not going to write the 10. I'm just going to just write it this way, over log of y. So log of x over log of y. So if I want to do the warm-up question of log base 5 of 125, I want to put that into my calculator. What I would do, since your calculator doesn't allow you to do that subscript, we do log of 125 divided by the log of 5. Now I will warn you, you might have to use parentheses around the bottom in case it doesn't, or you have to close that parenthesis off. So just kind of play around with that a little bit. It should be 3. So we want to get that out of it. It should be 3. So if you guys can try this in your calculator, so log of 125 over log of 5, you should get 3. Yes, if you're not getting 3, we have to figure out what you're doing wrong with your calculator. So what you just changed this to is rather than using log base 5, you changed it to log base 10. This same thing would work if you use the little ln button. That should give you the same outcome. You could use ln of 125 over ln of 5, and it would give you the same outcome. Okay? All right, did we all get 3? If you guys get that to work? How do you do it? So log base, or log of 125, and then close that parenthesis, and then divide by log of 5. Yep, you should get 3. All right, you done? And the reason for that is because 5 to the 3rd power is 125. So that's why I knew it would be 3, so I picked that just because it worked out nicely. A lot of times logarithms don't work out to be nice numbers. It's kind of crazy decimal or something like that. So this next one, so we're going to do here, is again log base 5 of 10 is not the default in our calculator. So they defaults to log base 10. So we're going to do log of what? Log of 10 over the log of 5. Now this time, I believe this is going to be a decimal because 5 to some power equals 10, and that is not, or 5, yeah, it's not a nice whole number. And you should be able to use this on a scientific calculator, like I just grabbed like the kind that I have here in my classroom, and we can do it on there. And so I got like 1.43.
Yep.
So a lot of times you're going to get answers like this. Next one, log base 8 of 1/2. And so I just want you guys to practice putting things other than nice whole numbers in there. So we're going to do log of 1/2. Again, that's in your calculator, over the log of 8. Now this one you might have to be a little careful about your parentheses. So you have to like maybe play around with that a little bit. And I think you should get negative 0.3 repeating. So it's like negative 1/3. So that allows you guys to use your calculator to do those logarithms if you actually want to evaluate the log. So these next few are asking us to solve for x. These first couple, not so bad. This last one is going to require a little bit more work, so we'll talk about those together. But see, sometimes using exponential equations to help us is going to be helpful in this case, because if you try to put this in your calculator the way it is, you can't put like an unknown in your calculator and have it solve it. So what I suggest doing, if you're ever stuck, try writing an exponential form instead. So that might be a good like hint to suggest here. Oops, not phone. Form. So try switching like 3a and b to exponential form first. question? So if you're stuck at all, I would, like we did in our warm-up, switch this to exponential form. So we start with the base. The new exponent is what the log equals. So I rewrote this in exponential form. Do we know how to do 3 to the 6th power? We do. So we should be able to solve this one for x using what we know about exponents. 3 to the 6th power I can do 729. So the x would be 729. Now if you're like, is that really right? You could now actually put that in. You could do log of 729 divided by the log of 3 and check it. You don't need to, but it should equal 6. This next one, what's our base? Base is x. So the 4th power would equal 81. Now this time, in order to figure out what the x is, what are we going to do? Not the square root, but what kind of root? Yeah, to get rid of that 4th power, we're going to use the 4th root. Oops, I should probably do it to each side. So the 4th root, so the x equals the 4th root of 81. So if you forgot where that is, it's probably in your math menu, those of you guys who have, but you might have to type the 4 first. Like on my calculator, I have to type the 4 first, and then I do the goofy root, and it should be like it's a root with a little x by it. It might be in your math menu. So
What's a math?
like there's a back button, and then it's like the 5th one down. But you might have to type the 4 first. So you have to get rid of that answer. So type 4 first. Does that work for you? Yeah. So 4. Oh, do 4 first.
Oh,
Sorry.
yeah.
Go back. Go back. Just completely clear it out.
And then you
So hit 4 first. Now math.
And then you go down.
Then you go down to like the 5th one, I think. And the 4th root of 81 is basically saying what number times itself 4 times going to equal 81, and what is that? 3. That might be just something you get to know just because we start working with these a little bit more. Did you find it? No, I bet it's on there somewhere. We can get it. All right. This next one is trying to get you guys to see that sometimes this expansion and contraction with our logarithms, sometimes putting things back together again will be helpful. So this one has addition of the same logarithm. So going back to the properties we learned today, what can I do with that? If it's the same logarithm and we're adding, what can we do? Change it to what? Yeah, it changes back to multiplication. So I can actually combine these two. So going back to our law, we're kind of doing the opposite of what we did on the front side. So since these are both log base 4, I'm going to write this as log base 4 as 1. And rather than addition, we're going to change it to multiplication. So x times x minus 6. So I combine that left side together. Now that might not seem very useful yet, but again, I remind you to switch things to exponential form. So in this case, our our base is 4. What's our power? 2. And that what is that going to equal?
X times x.
Yeah, it's going to equal whatever we're taking the log of. So what I just did with this is I just took the log out of this equation. So I broke it, I put them together, kind of simplified it up a little bit, and then I rewrote this in that exponential form. 4 to the 2nd becomes 16. If I distribute this in, this becomes x squared minus 6x. I'm hoping this looks somewhat familiar to you. Where have we seen this before today? Yeah, we can factor this, but in order to factor it, it needs to equal 0 first. So move this 16 over, and this is exactly our warm-up question, except we didn't solve it. So this will allow us to go ahead and solve this for x. Now, we're going to talk a little bit later about the domain of logarithms. We're not going to get in that too much. Technically, one of these answers would get thrown out because of the type of x values we can use, but so to get x squared, we're going to do x times x, multiply to get negative 16. So this is the same thing we did in the warm-up. But then if I would go to solve this, I would set each of those equal to 0, and I would get x is 8, and x is also negative 2. You'd solve those to set them equal to 0, if you guys remember that with factoring and solving. Now technically we would throw out the negative one, and like I said, we didn't get into that much or at all yet about the domains of logarithms, so we really just want that positive answer, but I'll talk to you guys later about that. That's a little much for today, I think. Alright, we're going to do the last problem. It actually looks longer than it is, and it's really similar to one of the ones in our homework, so I want to talk to you guys about it before we go. So a rabbit population grows. If you ever like any comments about how quickly rabbits reproduce, if you ever try to raise rabbits, I think that's pretty common. A rabbit population has grown at a rate of 5% per year over the past 10 years, and that's probably a little bit low. At this rate, how long would it take for the population to quadruple? What does quadruple mean? Times 4. So 4 times as big. All right, so we're talking about exponential growth. We're going to do our exponential equation. So if you guys remember, we talked about this one. Okay, we're going to put everything in that we know. We don't know what they began at. We actually don't care that this has happened over the course of 10 years. We want to know how much it's going to quadruple from today. Like, when will they be 4 times as big of a population? Do you guys remember we talked about when it was doubling? What did we do? What did we do to set this up? We did this a few days ago. If I said it just wanted to double, what would we set this equal to?
Double whatever it is.
Yeah, but what if we don't know the starting value? Remember kind of a shortcut we talked about with that? So if I said to double,
We should put like 2.
yeah, like so we had it like this or something like that. And so we said, oh, we're doubling that population, so why doesn't it just equal 2? What do you think this one's just going to equal? We want to quadruple it. It's just going to equal 4. So we're going to kind of take the A and the B out of this, where I kind of just know I want it to quadruple. I don't care how many rabbits I have to start with. I want to know when will it be 4 times as big as it was when it started. So E, and the past 10 years, I don't really care about the years in that case, so we don't want to use their years. We want to know now. A rate of 5%, so what's my rate going to be up here? 0.05. Now, previously we were doing the trace button to find the t. I'm going to teach you guys a quicker way to do this. Yeah.
Isn't the like rate? Isn't that like supposed to be annual? And it happened in the past 10 years. Wouldn't it be?
It said per year over the past.
Oh.
So it's like kind of, it was trying to, no, it's a good question. It was trying to establish like a pattern.
Okay.
So the fact that it's been 10 years or 50 years, it doesn't really matter. It's per year. Yeah, good point though. Thanks for catching. All right, now in the past we would just use the trace button. What I'm going to suggest is maybe let's try using logarithms. So let's change this to a logarithmic function. So if I'm doing the log, what's the base going to be? E. Now log base E is technically that ln. So again, that's why that ln is so important. We'll deal with that in a second. Log base E of what? 4 is going to equal 0.5t. So rather than having to do the trace button on our calculator, we can just use this. Yeah. Yes, they do catch me. Otherwise, they're doubling like by 50% per year, which maybe is closer to true for rabbits. I don't know. I'm the rabbit expert. Why aren't you erasing? Okay. Thank you. Okay. So log base E, rather than using log base E, we're going to use ln. That's it's the same thing. ln of 4 is 0.05t. So the good news is we can solve this for t. This is being multiplied, so we're going to divide by 0.05. So ln of 4, you're going to put in your calculator. ln should be really close to the log button. Now you probably want to close that parentheses off, because then you're dividing it by 0.05. And that's going to give us the number of years, which should be about 27. We'd probably round up to 28 years. That sound right?
Yeah.
So being able to use logarithms when we're trying to solve exponential, rather than having to just do the trace button all along our calculator and say, oh, when did I get there, and like doing this, over and over again, this allows us to solve those exponential functions. All right, so homework is listed there for you guys. We have about 20 minutes to get going on it.